Have you ever typed a simple phrase into an AI image generator like Cyberpunk Samurai in the rain, and just a few seconds later, this incredible photorealistic image pops up? It really feels like magic, right? But the real secret isn't some magic spell. It's this brilliant process of starting with pure random noise and turning it into a masterpiece. So let's break down how this actually works. Yeah, what you're seeing isn't magic at all. It's an absolute marvel of engineering called a latent diffusion model. I'm Dr. Vernette Grant, and in this explainer, we're going to pull back the curtain on the science and see exactly how these systems learn to create amazing art by literally starting with chaos and working backward. And look, this isn't some obscure niche tech we're talking about. This is the fundamental engine that powers the biggest names out there. The AI image generators you use every day, Stable Diffusion, Midjourney, DALL, they're all built on this blueprint. All right, first up, painting backwards from noise. This gets right to the core idea of diffusion. So how does it all begin? Well, at its heart, a diffusion model is basically a system that learns how to create order from total chaos. You could say it learns how to clean up a mess, and that's its secret weapon. So during its training, the AI is shown millions, and I mean millions of clean, clear images. Then the system starts to systematically mess them up. It adds noise, kind of like the static you'd see on an old TV. It does this in little steps, again and again, until the original image is just gone, totally buried under a sea of random pixels. This whole process is called forward diffusion. Now, here's where the magic really happens. This is where the learning comes in. The model is then trained to do the exact opposite, to reverse that process. It starts with just the pure noise, and it has to predict and subtract the static step by step to get all the way back to the original image. By doing this millions of times, the AI starts to learn the fundamental patterns of what makes a cat look like a cat, or a face look like a face. It's learning the very structure of our world. Next section, the speed problem. Because, well, the simple way is just way too slow. See, there's a massive problem with this whole approach. Denoising an image pixel by pixel is incredibly, mind-numbingly slow. A high-resolution image has millions of pixels, and running these complex calculations on every single one would take forever and cost an absolute fortune in computing power. This was the big bottleneck. For this technology to ever be useful for you and me, it couldn't just be possible in a lab. It had to be practical. It needed to be fast, and it needed to be affordable. And that was the challenge that required a seriously brilliant solution. And the solution they came up with? Whoa, it was a total game changer. What if you didn't have to work with all those millions of pixels? What if you could shrink the problem down by a factor of 48? This, my friends, is where the latent in latent diffusion comes in. This comparison right here is everything. Instead of working in that massive, slow, and super expensive pixel space, the model does all of its thinking in a tiny, compressed, and incredibly fast latent space. Honestly, this is the core innovation that unlocked modern AI image generation for all of us. Okay, next section, the latent space solution, and we need to introduce the VAE. The genius of this approach is that all the heavy lifting, all of that tough denoising work, happens in that tiny, compressed version of the image. And the tool that makes all this compression possible is called the VAE. So the VAE, or Variational Autoencoder, basically acts like a highly sophisticated zip file for images. It can take a large 512 by 512 pixel image and just squish it down into a tiny 64 by 64 latent summary. It keeps all the essential information, but makes the whole thing 48 times smaller and so much faster to process. So the workflow is pretty simple, but really powerful. First, the VAE's encoder compresses the image down into that small latent space. Then, all the hard denoising work happens right there, in that efficient little space. And finally, when the job is done, the VAE's decoder unzips the result back into the beautiful, full-sized image that you see on your screen. Okay, so we've solved the speed problem, which is huge, but there's another really important question, right? The AI is starting with a block of just random noise in this little latent space. How does it know to create our Cyberpunk Samurai and not, a picture of a duck? And that brings us to our next section, the AI's instruction manual, which is all about guiding the denoising process. This is where the final couple of components come into play. We need a guide, an instruction manual, to steer that whole process toward the image we actually want.
First up is the text encoder. You'll often hear about a model called CLIP. Its job is to read your text prompt, Cyberpunk Samurai in the Rain, and translate it from our human language into a precise mathematical vector. You can think of this as a set of coordinates on a giant map of ideas. This numerical code becomes the AI's set of instructions.
Next, we have the UNet. It actually gets its name from its U-shaped architecture and diagrams. This thing is the real brain of the operation. It's the actual denoiser. It looks at the noisy latent image and at the numerical instructions from the text encoder, and then it figures out how to remove the noise in a way that perfectly matches the meaning of your prompt.
Okay, last section, from prompt to picture. It's time to put it all together. So now we have all the pieces on the board. We have the efficient latent space, we have our text instructions, and we have the UNet denoiser. Let's see how they all work together in this beautiful feedback loop. So the process kicks off with random noise and your text instructions. The UNet then takes a small step, removing just a little bit of that noise. Then it checks back with the instructions, almost asking itself, am I getting closer to a Cyberpunk Samurai? It refines, removes more noise, and checks again. This loop repeats dozens of times, getting more and more accurate with each and every step. After about 20 to 50 of these refinement steps, that initial block of random static has been totally transformed. It's now a structured, coherent, latent image that is a perfect mathematical representation of your prompt, and it's ready for that final step.
So when you boil it all down, it all comes down to these three pillars. You have the VAE, which is the compressor, and that gives us speed. You have the CLIP text encoder, which is the guide, and that provides the accuracy. And finally, you have the UNet, the denoiser, which is the artist that does the actual work of creation. And that's really how latent diffusion models combine efficiency, guidance, and raw creative power to turn noise into art. I'm Dr. Vernette Grant, and I really hope this explainer helped clear up some of that magic for you. Stay curious and let me know, what complex AI concept should we demystify next?